also like to thank all of the Fellows of the Academy and especially my nominators and supporters for welcoming me into the Academy. I'd also like to acknowledge the only 2 employers I've had in my entire life. For the last 10 years I've been at Monash, and Monash University has provided a very supportive and exciting framework and environment in which to do research and teaching. So it's been great to become a teacher late in my life. Much of the work I'm going to talk about today, though, started in the 35 years I spent in the Bureau as a researcher in the Bureau of Meteorology. And having a strong research in-house capability in the Bureau of Meteorology has meant that there's been enormous improvement in the way we understand and predict the atmosphere at all timescales, from a very short-term weather of a couple of hours ahead, right up to climate change. I started as a weather forecaster, and at those days, everybody knew more about weather than the weather forecasters. And now I've evolved into a climate scientist, and now everybody, including every single politician on Capitol Hill, knows more about climate than I do. Now, I've really only specialised in mainly one particular area of climate. And we used to call this long-range weather forecasting when I was young. Now it's seasonal to interannual climate prediction, much sexier title. And much of the focus of my work has been on how do we use the El Nino Southern Oscillation phenomenon, ENSO, to make predictions of climate and climate impacts. Now, I think everybody here knows what an El Nino is, but just in case someone's just walked in and doesn't, I thought I'd just quickly describe what it is in these 2 slides. On the right is the sea surface temperature anomaly for February this year. The anomaly is the deviation of the actual sea surface temperature in that month from the expected sea surface temperature in that location in that month of the year. Where it's red or yellow, it's warmer than normal. And if you can see the patch that stretches from the date line along the equator towards the South American coast, that's basically the El Nino. That's the warm sea water that occurs every now and again. If you look on the left-hand side, that's 6 months ago, October 2015, you can see that there's a patch that's still there. It's the same patch, basically, slightly different shape. So that's one important aspect I'm going to be talking about. It's there in October, it's also there in February. We use a lot of indices to actually describe the El Nino. I'm going to use just one. All of the results I'm going to show would come up the same way if I used other ones, but I'm going to use this one which is called Nino 3.4, which is just the average sea surface temperature in that box that I've just shown. Now, if you look in those 2 graphs, those 2 maps, along in the tropics, it's all, on the right-hand one, the February one, it's all yellow or orange. Everywhere is warm, fairly typical of an El Nino by around February. If you look at the left-hand side one, it's almost all yellow, except for green patches between Indonesia and Northern Australia and around the Great Barrier Reef. That's also typical, and I'm going to get to that at the end of this talk, because it's important when we consider how El Nino and its impact might change. So I'll also be looking at the sea surface temperature averaged in that box. So why are we interested? Well, we're interested because El Nino events, and I should have said La Nina events, which just almost just the opposite colouring on those maps. If those maps where it was yellow, red and yellow, if that was green and blue, that would be a La Nina event. They cause climate extremes all around the Pacific and Indian Oceans. And I'll just do 2 examples. And I'm afraid I don't have pictures of coral trout or anything like that, or Nemo. I've got time series and scatter diagrams. The blue line here is the average rainfall over land over the maritime continent. Maritime continent, Indonesia, New Guinea, southern Philippines, and parts of Southeast Asia. Just averaged over the land stations, starting back in 1950, and it's just averaged in one particular time of year, June to November. The red line is the index of El Nino, the Nino 3.4 index, and the scale on that's on the right-hand side, and it's been inverted. So down here, the warm temperatures, these are the El Nino events, and that's the El Nino event we're in, or just been in, and there's the rainfall. It's been a dry year, dry June to November in the maritime continent. That has led to forest fires and haze, as it always does. You can see how strong that relationship is. So, in a sense, the sea surface temperature on one side of the Pacific is determining the rainfall over a huge area around north of us in the maritime continent. It also affects Australian rainfall, as I'm sure everyone knows, and I'll just illustrate this because I want to show its effect on wheat yield. Along the horizontal axis, along here, this is the Nino 3.4 temperatures. Up here are the El Nino events, the La Nina events down here, and this is the change in wheat yield from one year to the next. The sea surface temperatures index I'm showing there is just December, so that's a pivot month, really. You can actually look at how much the wheat yield is going to change based on just what the December sea surface temperature is. You see, I've drawn a horizontal line there, which is shows the years when there's been a substantial drop in wheat yield, averaged over all of Australia, and these are at the right-hand end of the graph, the El Nino events. An El Nino event drives a decline in wheat yield because of its effect on rainfall over much of Australia. So it has a lot of impact. But that doesn't alone give us a way of making a prediction. And I want to show how we can make predictions by showing the evolution of the last three big El Nino events. Green is 1982-83, red's 97-98, and blue's the one we're in now, 2015-16. We start in April one year, go through to here about the end of the year, we're about here in May, and go through to the end of the following year. They all show very similar evolution. And I've just drawn some vertical lines there to show May, or the April-May transition. And these three events, they're typical of most El Nino events. They start around May, they last about 12 months, they end around May. They rarely abort after June. If you've got an El Nino event starting by June, it usually proceeds and intensifies. I also want to note that these three events are of very similar intensity, and we'll come back to that right at the end of the talk. This is the same sort of graph, except this time I'm not just showing the three biggest El Nino events. These are all of the moderate to large El Nino events and all the moderate to large La Nina events, and they show the same thing. Show how they start to diverge around here or here, if negative sea surface temperatures anomalies if it's a La Nina event. And if you look at the difference between here, the end of the year, when these have separated quite dramatically, and that separation starts around here, but around March, April, May, it's a mess, it's a jumble. And we have a lot of trouble predicting how El Nino will develop, or even if it will have developed, from before about May. And we call that the predictability barrier. And that's one thing which a lot of people are still working on and working very hard at, trying to develop models that can predict months before that predictability barrier how we're going to go. It's a very difficult thing to do. I mainly focus on what we can do after that predictability barrier. So this is the illustration of that predictability barrier. It's an attempt to predict sea surface temperatures 6 months in advance. So along here we've got the December Nino 3.4 index. Each of these dots is 1 year over the last 60 or so years. Here is the June following that December, and you can see there's not much relationship at all. It's a pretty much random spread. So a La Nina in 1 year in December doesn't tell you it'll be in a La Nina or an El Nino in June, 6 months later. So it's difficult to predict the onset of an El Nino because of its predictability barrier. This is the same thing if you change that around, though. If you use the June Nino index to try to predict the subsequent December index, you see a very strong relationships. So an El Nino that occurs in December has already been foreshadowed at least by June, 6 months earlier. So that makes it relatively easy to predict impacts that are related to the El Nino that happen after June. And I'll just talk about one of them. This is tropical cyclone activity around Australia. Tropical cyclones occur December to April. We can count how many there are, and you can predict them as early as June the previous year. You can predict how many tropical cyclones are going to occur around northern Australia in the following December to April. This one uses September to November, Nino 3.4 down here, up against the numbers of tropical cyclones. I've taken year-to-year differences because there are non-climate trends in the tropical cyclone activities. But you can see what happens. El Nino, we have few tropical cyclones. La Nina, we have lots of tropical cyclones. There are lots of other examples. You can predict Great Barrier Reef bleaching, drought and fire over New Guinea, Indonesia, Australia. Crop yields are shown, heat waves, arbovirus epidemics, lots of things that are related to climate that occur towards this end of the year. Okay, so the second part of the talk, much quicker. How is global warming affecting the El Nino? That's what's happened up till now and is happening now. How is it going to change in the future? This shows global warming in one slide. The dark line is annual global mean surface temperature, increasing about a degree since about 1880. The red line is measurements of carbon dioxide at Mauna Loa in Hawaii. The blue diamonds are measurements of carbon dioxide in air trapped in ice core at Law Dome, taken by the Antarctic Division and studied by CSIRO. You can see the 1 degree warming has come about because of about a third increase of carbon dioxide in the atmosphere since pre-industrial times. So, how is that changing the El Nino? Well, I pointed out those 3 episodes were all about the same intensity. So there's no suggestion there that the El Nino is becoming more intense or less frequent, but it's changing, it's operating now in a different background. And this shows for those 3 big events, starting with the green one, the earliest one, 1982-83, the 2 years of global land-ocean temperatures. And you can see how for each of them, the temperature, the global temperature, increases as we progress through to about now, or through to the end of the year, January. So back here is not much of an anomaly, but by the time we get here, the temperature is about half a degree warmer. And each of those does the same progression, but they've all been stepped up. So every 15 to 20 years, we're getting another big El Nino, but it's starting from a warmer baseline. So what's happening is climate change is affecting the way that operates, the way they impact. And so how will that affect us? Well, this is that little patch of sea surface temperatures in the north of Australia. And in the past and up till now, sea surface temperatures around northern Australia have been very cold during it at the start of an El Nino, as shown this one here. But global warming and regional warming is affecting that. So the warming is altering the impact of El Nino. We don't know exactly how. CSIRO has been leading the work on that, but whether that work will continue, we don't know. So there's 2 ways to use El Nino and La Nina, the hard way or the easy way. We're not getting nearly enough out of even the easy way yet. This is a simple introduction to El Nino. Andrea Tacheto tomorrow will talk about the more complicated aspects of it, but I'll stop there. Thank you very much.
Are there any questions or comments? Ross?
Just looking at those predictions of cyclone numbers, it suggests that insurance companies could set their risk premiums at an optimal time in the year.
Insurance companies know a lot about El Nino, as they know about climate change also.
Go ahead, John, here.
Is the poor prediction for yield correlating with El Nino because you're averaging yield across Australia? If you broke it into smaller parts of the country, would the predictions be different?
Yes, if you look just, say, the Murray-Darling or Eastern Australia, because the relationships with rainfall are much stronger there than in the west, then the relationship becomes a bit stronger. Yeah.
Any further questions? I have a question. Okay, go ahead. Michael, okay, you can go ahead.
What's your opinion as to why it is that all politicians know more about climate change? Why is this a topic in which people just ignore the science?
I knew a minefield question would turn up. Everyone experiences the weather and the climate. There are three big predictable climate signals at human timescales. There's the annual cycle, and we all use that to decide where we're going to go skiing, for instance. We all use that. But they have heard about El Nino, and their local experience is they really can't feel a long-term change in climate. So I think there are lots of reasons why people do think they know a lot about climate. It's difficult to actually extrapolate from a single person's experience in a single location to something as arcane as a global temperature anomaly. I think it's almost as simple as that, coupled with the fact that everybody's an expert on weather too, and climate's just the aggregation of weather.
On that note, could you please join me to thank Neville Nicholls?